Okay, so if you look at the back side of your notes, you're going to be able to see the equation that we're going to use to calculate delta H for this type of enthalpy change. Remember, again, enthalpy is a state function. We already learned a bunch of different ways to calculate delta H, and this is just yet another way to do that. The same rules apply as we learned before. You know, a negative delta H is exothermic, a positive delta H is endothermic. Now, one thing that's kind of weird with this delta H equation, we've learned in the past that delta means final minus initial, and that is true of every single time we use delta except this one. This is an instance where delta actually is the reactants minus the products, which might seem strange because, like we've learned before, delta is supposed to be products minus reactants. But the reason why it's formatted like that is because of the information that we're going to use. If you remember from the front side of the notes, we're using these bond energies. And the bond energies are listed as the energies to break bonds. So they're all listed positive. And because of that, the equation doesn't work if it's final minus initial. So they wrote the equation initial minus final to account for that. And so we, of course, have to use it that way. So again, the equation says delta H equals the bonds broken minus the bonds formed. Remember, the bonds broken are on the reactant side because we're going to be breaking bonds of all of the reactants, and then we'll be subtracting the energy that gets released when the new bonds are formed, which would be on the product side. So please commit to memory that this is the time when delta is actually reactant minus product instead of product minus reactant. So to do these problems, we're going to have to draw out our structures. Now on your paper, all you see is the equation. You can see here that I've drawn out all the structures. So if you want to pause the video and go ahead and draw those out, you can either do them for yourself or just copy what I have. If you've been struggling with your structure drawing, I would suggest you trying them yourself and just pause it and come back. So what we're going to do with all of these is we're going to look at each bond individually. And on the reactant side, we know we're going to break all of these bonds. And on the product side, we know we're going to reform these bonds. And if we take into account all the energy it took to break these ones and all the energy it takes to reform these ones, we can actually figure out what the overall enthalpy change was. Might have taken more energy, might have released energy. We're just not sure at this point. So we'll start with this methane molecule. We're going to add up how much energy it takes to break up this entire methane molecule. So we're going to start by saying that delta H is equal to, now remember, we're starting reactants minus products. So the reactants, again, the CH4s we're going to start with. We have 4, so I'm going to do 4 carbon-hydrogen bonds to break, carbon-hydrogen single bonds. So if you flip over to your table on the other side, we find carbon-hydrogen bond energy is 413. You see right here and right here. So 413. So we're going to have to do 413 4 times in order to break up that whole methane molecule. So this right here represents the carbon-hydrogen bond, and then the 4 represents how many we have of them. Then we're going to add to that the energy to break up one bromine-bromine single bond. If you look on your front table, I'm going to stop flipping back and forth, but you can flip. The bromine-bromine single bond is 193 kilojoules per mole. And I only have one of them, so I'm only going to do that times 1. So that's the reactants. I need to break those 4 bonds and that bond. So this is all of my reactants. Then I'm going to close parenthesis that and then minus, and then I'm going to start a new parenthesis for all of these bonds. Okay, so it's going to be subtracting the product ones. So on the product side, I have 3 carbon-hydrogen single bonds. So I'm going to do 3 times the carbon-hydrogen single bond length, which we looked up to be 314. Okay, and we also have a carbon-bromine single bond, so we'll look that value up on the front. Carbon-bromine single bond is 285. And then we also have a hydrogen-bromine bond, single bond here. We look that up on the front, and it is 366. So I close parenthesis that. So this one was the carbon-bromine. This was the hydrogen-bromine. You don't have to do those notations I just put on the top, but if you want to, just to make sure you're accounting for everything, then that's fine. So if we plug all of that into our calculator, we will get a final answer of negative 45 kilojoules. Now notice the unit on the table on the front was in kilojoules per mole. Kilojoules per mole. Yet when I just got this final unit, I just did kilojoules. So where did the moles go? Well, remember these coefficients we're using. We're saying we have 4 moles of this. We have 1 mole, 3 moles, 1 mole, 1 mole. Those mole ratios that are shown in our balanced equation are accounting for the moles. So the mole part of the unit is canceling out. So your delta H final answer will be in kilojoules. So we can go ahead and try the second example. Like the last one, if you want to pause it and draw out your structures, it's important that you draw them out and you don't just look at the equation as it's written, because you can't tell things like oxygen is supposed to have a double bond. And remember, on the front table we have a single bonded oxygen. Oxygen is different in energy to break than a double bonded oxygen. So you have to pay attention to all of that. So we're going to start here with our 2 H2 molecules. Now notice I drew an H2 and then I put a 2 outside here because the coefficient was saying that you needed 2 H2s to react with an O2. And those coefficients are important. So we're going to do 2 hydrogen, well, start with delta H equals, and we'll do 2 hydrogen-hydrogen single bonds. So you look up hydrogen-hydrogen single bond, and that is 436 kilojoules per mole. So that's the hydrogen-hydrogen one. And then I have an oxygen-oxygen double bond. Don't look at the oxygen-oxygen single bond. Look on your front table down at the bottom. The oxygen-oxygen double bond is 498. Okay, so this is the oxygen-oxygen double bond. So we accounted for all the bonds on the reactant side. Now I'm going to subtract all the bonds on the product side. So I have 2 water molecules. Now each water molecule, look inside this parenthesis, has 2 oxygen hydrogen single bonds, but we have 2 water molecules. So it would look like this if we drew it out over here. So if you were to count up how many bonds you need to break, you would need to break 1, 2, 3, 4 hydrogen oxygen single bonds. So I'm going to do 4 times the hydrogen oxygen single bond, which the table tells you is 463. So this is the hydrogen oxygen. Okay, and that's all of the bonds that we have in this molecule, so we can plug that into our calculator and we get a delta H of negative 482 kilojoules. Once again, your unit is going to be just kilojoules, not kilojoules per mole. Also, sig fig wise, we're doing addition subtraction only, so the rule for addition subtraction stands, so it should be least number of decimal places, which is pretty easy because if you look at the table, they're all in whole numbers. So we'll try some more problems with this in class, but the key is you have to draw the structures out so that you can actually see what bonds are being broken and what bonds are being formed.